sometimes a function is defined only to the right or to the left of the point at which we are taking the limit. In that case, we need the notion of one-sided limits. The idea is quite similar to the notion of a limit. So, suppose we have a function f from I to r, where I is a subset of R, and let us say we have some point A that we are interested in, and I contains an interval of the form a comma b, where b is greater than a. So, this function is defined just to the right of the point A. And now we can talk about this function having a right limit at A. So, definition, we say that the right limit, which we denote by limit as x goes to A plus. So, this means x approaches A from the right of f of x is equal to L if, and the definition is almost the same as that of limit. So, we would say for every epsilon greater than 0, there exists delta greater than 0, such that, now in the usual notion of a limit, we had this absolute value of x minus a less than delta, but here we do not have that, we just have x minus a less than delta. We will only look at x to the right of a. So, 0 less than x minus a less than delta implies that absolute value of f x minus L is less than epsilon. In order to talk about the left limit, we just need to change the definition of the right limit, which I have copied again over here, make a few minor changes. So, firstly we need the function to be defined a little to the left of the point A. So, let me change this to b comma a, where b is less than a. We say that the limit as x goes to a from the left of f of x is equal to L if for every epsilon greater than 0, there exists delta greater than 0, such that, and now we are looking at points that are to the right of a. So, to the left of a. So, we should say a minus x implies that f of x minus L is less than epsilon. Now, one of the reasons we are interested in left limits and right limits is we want to talk about continuity, right continuity and left continuity of functions. So, in the same spirit, we can define a function to be left continuous or right continuous. So, suppose f I to r is a function, I contains now let us say the closed interval a b, where b is greater than a. So, we are assuming that f is also defined at the point A and to the right of A. Then we say that f is right continuous at A if, as you would have guessed, the right limit as x approaches A of f of x is equal to the value of the function at the point A. And as before, you can change this definition of right continuity to left continuity. So, we say that if the function is defined on b to closed A, where b is less than a, we say that f is left continuous at a if the limit as x approaches a from the left f of x is equal to f of a. Now, what this allows us is to define continuous functions on a closed interval, which we will need for what comes next. Definition: a function f on a closed interval a b is said to be continuous if firstly f is right continuous at A, it is continuous on the open interval A comma B, which means it is continuous at every point x strictly between A and B, and thirdly f is left continuous at B. One of the most important theorems involving continuous functions is called the intermediate value theorem. I will give two versions of this theorem. First, I will prove a somewhat simplified version of the theorem, but you will see it is almost the same as the more general version, and so it is called the intermediate value theorem. Let me call it version 1. And what it says is that if f from the closed interval a b to r is a continuous function, such that f of a and f of b have opposite signs. So, maybe f of a is negative, in which case f of b should be positive, or f of b is negative, in which case f of a is positive. So, the signs at the endpoints are opposite. Then you can find a point in between. There exists a point x naught strictly between a and b, such that f of x naught is equal to 0. Now, this might seem like a completely obvious statement, right. If something is continuous, I have a function that is continuous, I would draw its graph at the point a on the closed interval a b. I know that its value at a is say negative, and I know that its value at b is positive, and I have to draw the graph. I could try to draw the graph of this function, and it would go from this negative value to the positive value. Somewhere it must cross the x axis somewhere in going from below the x axis to above the x axis. But this is not a proof, this is just an intuitive idea of why this theorem should hold. And in fact, it is not even true if you were to replace the closed interval a b by the rational numbers that lie between a and b. This is something we will talk about at some other time in the examples. So, in fact, this theorem relies very much on the axiomatics for real numbers, and it requires a proof, which I will now give you. The proof will be somewhat constructive in the sense that we will try to find this point where it is equal to 0. We will look for it and we will find it. In fact, find it in the sense that we will find a sequence that converges to this point maybe. So, let me start on the proof. So, the idea of the proof is somewhat similar to the proof of the Bolzano-Weierstrass theorem. So, you have this function here, let us just use this picture itself. So, over here it is negative, and over here it is positive. So, what I will do is I will divide this interval into two parts, two equal parts. So, I will take C to be the midpoint of A and B, and let me look if the function is positive or negative at C. If the function is positive at C, then that would mean that the sign has changed between A and C. In this picture, the function is negative at C. And what that means is that the sign has changed between C and B. And so, now I have the same situation that I had initially, that the sign of the function had changed between A and B. Now, I have that the sign of the function has changed between C and B, but the length of the interval from C to B is half the length of the original interval from A to B. So, the idea is we will repeatedly keep dividing this interval into halves, and we will find smaller and smaller intervals on which the sign changes, and from that sequence of intervals we will find a point where the function must be 0. So, let me just show you the first step. So, we will construct these sequences. So, let A1 be equal to A, B1 be equal to B, and now let us let C1 to be the midpoint. So, that C1 is A1 plus B1 by 2. Now, there are 3 possibilities. If f of C1 is equal to 0, well, then we are done. We can take x 0 to be just C1. Otherwise, there are 2 remaining possibilities. If f of C1 is greater than 0. Okay, so, here I am assuming that f of A is less than 0 and f of B is greater than 0. If it were the other way around, we could just take minus f instead of f, and then f of A would be less than 0 and f of B would be greater than 0 once again. But if f is continuous, minus f is also continuous. So, we could apply the result to minus f. So, I am assuming here that f of A is less than 0, f of B is greater than 0. And so, now if f of C1 is greater than 0, then what is happening is that f of A and f of C1 have opposite signs. So, let A2 to be the same as A1, B2 to be C1. What we have is f of A2 is less than 0, which is less than f of B2. And moreover, the distance between B2 minus A2, this is the half the distance between B1 minus A1, which anyway is just B minus A by 2. Now, we will repeat this process having constructed A n and B n, and we will assume that f of A n is less than 0, which is less than f of B n, and also that B n minus A n is equal to B minus A divided by 2 to the power n minus 1. We will construct A n plus 1 and B n plus 1. So, firstly you let C n be A n plus B n by 2. If f of C n is equal to 0, then you can take x naught to be C n. Otherwise, if f of C n is positive, then you take A n plus 1 to be A n, B n plus 1 to be C n. If f of C n is negative, take A n plus 1 to be C n, B n plus 1 to be B n. So, what is happening here is that we have A n, B n. We know that the function is negative over here, we know that it is positive over here. We took C n to be the midpoint, and then in case the function is positive at C n, then we know that it changes sign between A n and C n. And so, we took this A n plus 1 to be A n in this case, and B n plus 1 to be C n, right. And so, what we have is that f of A n plus 1 is less than 0 is less than f of B n plus 1, and of course, b n plus 1 minus a n plus 1 is equal to b minus a divided by 2 to the power n. And you can do the same thing in the other case where f of c n is negative. So, if f of c n were negative, then we know that the sign changes between c n and b n. So, we would now take a n plus 1 to be c n and b n plus 1 to be b n. And once again we would have f of a n plus 1 is less than 0, but f of b n plus 1 is greater than 0. And once again the distance between b n plus 1 and a n plus 1 would be half the distance between b n and a n, which would be b minus a divided by 2 to the power n. So, what have we done? I have given you an inductive process which will either at some finite stage arrive at a point. So, there is this case where f of c n is 0. So, it will arrive at a point where the function takes value 0, in which case we can take that point to be x 0. Otherwise, so if f of c n is not equal to 0 for all n, then we would have constructed two sequences. The first sequence is a 1, it is an increasing sequence less than or equal to a 2 less than or equal to a 3, and this sequence of course is bounded above by b, and another sequence b 1, this is now a decreasing sequence, and this is bounded below by a. And what we know is that f of a n is less than 0 for all n, f of b n is greater than 0 for all n. And moreover, if you take the difference of these sequences and take the limit as n tends to infinity, well, this is just limit as n tends to infinity. We know that b n minus a n is b minus a divided by 2 to the power n minus 1. So, this goes to 0. Now, this is a weakly increasing sequence that is bounded above. So, it has a limit. The second is a weakly decreasing sequence that is bounded below. So, it also has a limit, and so these limits by the difference of limits, this is limit n tends to infinity a n. Therefore, these two sequences have the same limit, let us call it x 0. And now I claim that f of x 0 is equal to 0. So, let us prove this. Given any epsilon greater than 0, choose delta greater than 0 such that if x minus x naught is less than delta, then f x minus f of x naught is less than epsilon. We can do this because f is continuous at x naught. Secondly, find n large enough so that b minus a divided by 2 to the power n minus 1 is less than delta. Now, let us look at this relationship between x 0, a n and b n. So, x 0 is the limit of the increasing sequence a n, and so each term of the sequence is somewhere to the left of x 0. It is also the limit of the decreasing sequence b n. So, each term of this sequence is to the right. And now, this distance between a n and b n, well, this is less than delta. Okay. So, what can we say? Well, certainly b n minus x 0, that is greater than 0, and that is less than b n minus a n, right, which is b minus a divided by 2 to the power n minus 1. And so, that is b minus a divided by 2 to the power n minus 1, which is less than delta. Therefore, we have b n minus x naught is less than delta, which implies that f of b n minus f of x naught is less than epsilon. We can rewrite this as saying that f of x naught, well, it lies between f of b n minus epsilon and f of b n plus epsilon. So, but certainly it is greater than f of b n minus epsilon, but f of b n itself is positive. So, this is greater than minus epsilon. Similarly, we have a n minus x naught is less than delta, which implies that f of a n minus f of x naught is less than epsilon. So, f of x naught is less than f of a n plus epsilon, but f of a n is less than 0. So, this in turn is less than epsilon. What we have shown with these two arguments is that f of x naught lies between minus epsilon and plus epsilon, i.e., absolute value of f of x naught is less than epsilon for all epsilon positive. And you know what this means? This means that f of x naught is equal to 0. Now, let me state the more standard formulation of the intermediate value theorem. Which here I will call version 2, and what it says is that if f is a continuous function on a closed interval a b, and y naught is any real number that lies strictly between f of a and f of b. Then there exists a point x naught between a and b such that f of x naught is equal to y naught. Now, this theorem is more or less the same as the previous theorem. All you have to do is let g of x be f of x minus y naught. Since f of a and f of b lie on opposite sides of y naught, the sign of g of a and g of b will be different. And so, you can apply the first version of the intermediate value theorem to the function g in order to prove the second version of the intermediate value theorem to the function f.